Mending neural implicit modeling for 3D vehicle reconstruction in the wild.
Reconstructing high-quality shapes from partial single-view observations is an important task for applications in vision, graphics, and robotics. However, it's extremely challenging. Recently, deep implicit modeling has shown promising results for 3D object reconstruction on synthetic or dense data. It learns a continuous implicit function in the 3D space to represent high-quality surfaces. It is powerful, high resolution, and easy to learn, but it has not performed well on real-world partial data. We first carefully analyze the prior works and highlight their limitations. Feed-forward implicit modeling approaches directly learn to map the input sensor data to a lane shape representation, which is implicitly decoded into an output mesh. These approaches are usually robust to observations with noise. However, they do not ensure that the predicted shape matches well with the observed real sensor data. This can cause poor performance. Compared to feed-forward approaches, deep optimization-based approaches generally deploy an autodecoder framework, where a lane code or network is iteratively optimized at test time according to sensor data, ensuring high fidelity with the input observations. However, these approaches do not perform well on in-the-wild real data, as the optimization can generate latent codes that are out of distribution, producing bad output shapes. They are also unstable with respect to the lane code initializations. And because they utilize handcrafted objective functions to optimize the 3D shape individually for each 3D point, they lack global shape consistency. We now address these limitations and propose a simple yet effective shape reconstruction approach. We first adopt the encoder module from the feed-forward approaches, which acts as a robust initializer for the lane code. Next, from the deep optimization approaches, we perform test-time optimization on the lane code. To ensure global shape consistency, we introduce a discriminator module which operates on the SDF volume as a whole, thus acting as a learned high-dimensional shape prior. Finally, we introduce a curriculum learning strategy to train the entire shape reconstruction framework, enabling us to effectively learn multiple shape priors. This allows our model to generalize to unseen real-world data in the wild. We now show evaluation results on two shape completion datasets, KITTI and North America. We perform either LiDAR completion, image reconstruction, or image plus LiDAR shape completion, and use the bounding box aggregated point cloud as ground truth. We began with showcasing LiDAR-based shape completion. Our approach is able to extract the global structure of the 3D shape from sparse and noisy sensor observations. Compared to the feed-forward approaches, we register well with the ground truth shape. And compared to deep optimization approaches such as deep SDF, we ensure the output shape maintains fine details and has limited artifacts. We now showcase LiDAR completion on the KITTI dataset. Compared to the North America dataset, KITTI observations are much sparser and noisier. Despite this noise, our approach maintains the fidelity standards. Compared to prior works, our approach better handles the sparse observations and generates shapes with fewer artifacts. For example, check the curvature of the back of the reconstructed cars. Our proposed approach is easily adaptable to other sensor data. Here we show shape reconstruction using only the image. Our method produces shapes that outperform the state-of-the-art DIST approach. We perform well in occluded scenarios. We can also better handle unusual vehicles, and our approach still has fewer artifacts. With our regularized optimization, our approach does not fail catastrophically. Finally, we showcase image plus LiDAR shape completion results on the North America dataset. Despite training the image and point cloud encoder separately, our proposed multi-code optimization combines them effectively to generate natural-looking shapes, even in challenging scenarios. This results in higher fidelity and finer details compared to the existing methods that also use both sensor data. Here's one more example. Notice a reconstructed sunroof on this Mercedes-Benz.